Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today we will show modeling and analysis of a cylinder. While analyzing, we'll use SolidWorks. Here we'll do two types of analysis, like complete model analysis will be there. By the same time, we'll have the segmented model, that is 1/4 part of the model will be taken and we'll apply symmetric boundary conditions to go for analysis. And our aim will be to compare both the results and see that both the cases we are having similar type of results, right? We have to model this cylinder, right? Using SolidWorks, we have to do it. Okay, we are starting this model right now. First of all, you have to take a radius, two concentric radius of 170 millimeter and 163 millimeter. Okay, let's start. Starting from new part. Okay, and you can see here the basic unit is like default unit is millimeter gram second. You can see at the lower right corner. If you like, you can change it also, but default mm/gs is better one, right? Okay, you can change it if you like. Okay, now for drawing this, we have to take the front plane and normal to. Let's start from a sketch. Initially, we have to start with the central line, and we have to draw two concentric circles. Not circles, you have to draw two concentric arcs. Let's draw the arcs. One, another one to be drawn. Okay, we'll start from here again. Two arcs you have drawn. Let's get the diameter of this one. From smart dimension, you can check the dimension. Here it is. How much it is? It is hundreds. We'll see the drawing again. The dimension was 170 and minus 7 to 170 and 163. 170. Diameter is 170 millimeter. Okay, and the diameter of this one, if you check, diameter of this one is 116 millimeter. So we'll take this again. Is 116 millimeter. And 16 millimeter. Next part, from here to come down 7 millimeter. So take the distance from here to here 7 millimeter. Is 7 millimeter. Done. Okay. Now this part, how much is the diameter? This part is having diameter 66. Okay, let's take it 66. From here to here is 66. Done. Now here to come down and draw some lines. We'll start from lines. First of all, we will provide dimensions to this one. Next, we will apply relations to make the other things. Smart dimension of this one is 10 millimeter. And this part all will be 5 millimeter. This one also 5 millimeter. This one also 5 millimeter. Right, done. Next part, what we'll do is we'll make the same thing but apply some relations to make the other things, right? We'll make the things without any dimension, and to get the proper dimensions, we'll apply relations. Done. 4 things you have done. Now we have to apply relations to these things, right? Now let's apply some relations to find the difference between, to make all the lines equal. First we are taking these vertical lines. This one, this one, this one. All are equal, right? Another line will be equal, so that one we didn't do. Another lines, another same type of things we have to draw. Okay, right? So again this one and that one will be equal. Length equal to 5 millimeter. All vertical lines of 5 millimeter. Similarly, right hand side also have to make all vertical lines equal and 5 millimeter. First provide my dimension to this one as 5 millimeter. Then we can provide relations that all these lines are equal. Okay, all these lines are equal. Now the horizontal lines have to be made equal. All are equal, right? And the equal length should be 5, that one not given, right? This is done. All are equal, but this length you have to provide as 5. Okay, done. Drawing is complete right now. Here, next part is what you have to do is from here to come down a little bit. Move little bit of inside. And join this part. Next is we have to provide dimension to this one, right? Let's see the drawing. Drawing is from here to here is 100 millimeter there. That is, this is having diameter 100 millimeter. This one to that one, 100 millimeter. Done. Next part, this one is 30 millimeter. Complete. Let's see the drawing again. Yeah, this 30. This is all okay, right? Fine. And the total length from here to here is 110. From the total length from top point to this one is 110. Again, dimension here to here 110. Done. One thing is remaining, that means we have to make these drawings complete. That means this is discontinuous, you have to make it continuous. So join this line, drawing is complete, it is a complete drawing. Now exit from the sketch and select the sketch, and from features you apply revolve was best. Okay, done. Our cylinder is ready, right? This will be ready for analysis. Now one thing we can do, this sketch looks odd, we can make this one hidden. Sketch, we make it hidden. Okay, done. Now to have a better view, we can do another thing, we can change the background a little bit. It will be plain white, it will look better. Okay, this looks better. Now we have to go for analysis. It will come from simulation, new study, and it is showing static ones. We are going for static structural analysis for the complete model. At the beginning we will go for complete model, and next to that we will make the segmented one. We will make 1/4 of this model and go for analysis. Right. First one is static structural analysis, green check. Next part we have to apply material. Now we have to consider that it will be aluminum alloys, right? So we can select alloys as aluminum alloys. And which grade should we select? Let's take the grade as aluminum. (214) alloy. Okay, it is having modulus of elasticity 73,000 Newton per millimeter square and Poisson's ratio 0.33. Apply. Okay. Right. Next part is you have to fix the model. That is, you have to fix the base part, and you have to apply load of pressure on the top part. Right. So we are selecting fixture. Fixture we are having a lot of options like fixed geometry is also there and also advanced geometry. Better to select advanced fixture. In advanced fixture, a lot of options are there like symmetric boundary conditions, cyclic boundary conditions, but here we require on flat surfaces. This one, select the flat surface, and here we have to select this. Now what we are planning to do is this flat surface should be having zero displacement with respect to radial direction, with respect to circumferential direction, and with respect to normal direction. Right? Let's do that one. The first one we are selecting, that means along phase direction it is having zero displacement. Along phase direction, that means you can see it is in radial direction, it is having zero displacement. Right? Okay. Next part we have to go for circumferential direction, zero displacement. Now finally we will go for normal direction, displacement is zero. That means the base is fixed from all the three different directions: normal direction, radial direction, also circumferential direction. This is fixed, right? Okay. Next part is you have to apply load of pressure on the top plate. It will come from external load, pressure. Unit of pressure is Newton per meter square, that will be changed to Newton per millimeter square, that is megapascal, right? Okay. And the unit we are the load value we are planning to provide, maybe we will apply 10 megapascal. Let's see whether it is failing or not. 10 megapascal we are applying load on that top plate. Okay, load is applied. Now the last part is mesh and run. Solution is initiated, is going on. Okay, we got the results, right? Okay. Now it is showing yield strength is 9.6 10 to the power 7 Newton per meter square, and maximum stress developed equal to 1.33 into 10 to the power 8. It is not safe. It is actually failing, right? Okay. That means 10 megapascal what load we have applied. This is very high. We have to reduce the load, right? Okay. We'll go for analysis again by changing the definition of load. External load we applied 10 Newton. Edit definition. Maybe we will apply a little bit of less load. Let's apply 5 megapascal load. Okay. Then mesh and run again. Yes, it is right now, it is safe. So yield strength is 9.6 10 to the power 7 Newton per meter square, and on meter stress is 6.68. Better to change the unit. We can change the unit to edit definition by changing the unit, and 1 meter stress unit is Newton per millimeter square megapascal. Okay. Now you can see yield strength is 96.5 megapascal, and bond measure stress developed is 66. So it is safe. Now how much is the modulus, how much is the factor of safety? It is equal to yield strength divided by bond measure stress. So we can see 96 divided by 66, it is almost near about 1.5. Let's see this one. We can produce this one from this result advisor also. New plot, factor of safety. Okay, it is showing minimum is 1.44 and maximum is 157. Maximum is very high, that is wastage of material, but we cannot do anything here. Minimum is 1.44, it is good enough, right? Okay. Now our task is to see whether this value is applicable when we are going for segmented portion, whether it will be same value or not, that will be checked. That means we want to apply symmetric boundary condition and see whether the results obtained for the complete model, is it okay with the segmented model. You can remember the values, comparison results. You will see the comparison results. The left hand side we are having bond measure stress equal to 66 megapascal, yield strength is 96 megapascal. Down we can see displacement, maximum displacement is equal to 7.4 into 10 to the minus 2 millimeter. Actually we are not bothered about this one. Our task is to see the stress level. Right hand side you can see strain and bottom side you can see factor of safety. Minimum factor of safety is 1.44 with the complete model. Exiting from the comparison, you can check the value of factor of safety 1.573 10 to the 2 maximum and minimum is 1.44. Okay, next part we have to go for segmental model. So we will go for model. This is the initial model. We have to cut the model into 1/4 of segment. So we're cutting from insert, cut with surface. Now we can select the surfaces with respect to front surface. Let's cut it. Okay, we got the half portion. Again, we have to cut it to make it 1/4. Again, insert, cut with surfaces. So which portion is equal? Right plane is equal. Right plane select. Okay, it is 1/4 portion. Now we got the model 1/4 model. Here also we have to apply the same thing, but our boundary conditions will be segmented boundary conditions and see whether the result is okay or not. This is having a lot of advantages because if the model is very complex and definitely it should be symmetrical. If the model is complex, then with segmented model we can have the result within a very short time and also meshing will be perfect. Some case it may so happen if the model is very complex we cannot generate perfect meshing. Let's see this analysis. So simulation, new study, it is showing static structure analysis 2. We are going for second analysis. Next part we have to apply material. So apply material. Initially we applied aluminum alloy. Here in this case also we have to apply same thing. Which alloy we applied? We applied 2014 alloy aluminum with modulus of elasticity 73,000 Newton per millimeter square and Poisson's ratio 0.33. Apply, close. Material is applied. Next part is fixing. Fixture, advanced fixture. Now one very important part is we have to apply symmetric boundary conditions, right? That means as it is segmented one. So we select the symmetry and the symmetric surfaces wherefrom we cut that object. Surfaces have been selected. Okay. Another thing, we have to fix this one from the bottom side. So what we'll do is again fixture, advanced fixture. We'll select the flat surface and bottom face you have to fix it. Select the bottom face and this should be fixed with respect to 3 different conditions. With respect to radial direction it will be having 0 displacement. With respect to circumferential direction it should be 0 displacement, and also with respect to normal direction it will be having 0 displacement. right? So green check, bottom part is fixed. Boundary conditions applied perfectly. Next we have to apply the load or pressure. It will come from external load, pressure. Unit of pressure we have to apply Newton per millimeter square, that is megapascal, and we applied 5 megapascal load. Okay, that to be applied on the top surface. Okay, load applied, done. Now the last part is mesh and run. Is running, a result is being generated. Let's see the result. Okay, we got the result. What it is showing yield strength is 9.6 10 to the 7 and our bond measure stress developed maximum is 6.8, right? So better to change the unit to megapascal. We can change it from edit definition. Okay, one measure stress, it is Newton per millimeter square. Okay, now let's compare the results. Yield strength was 96 megapascal and the maximum stress developed equal to 68 megapascal, right? It is almost same what we got before. Let's see the value of our factor of safety. This can be obtained for result advisor, new plot, and factor of safety. Okay, yes, it is 1.4. Minimum is 1.4 and maximum is 1.67 10 to the 2. Initial case we got the factor of safety, it was 1.44. Now it is 1.409. It is almost same. So in both the cases we got similar results. Stress developed same, and also displacement and other things we didn't consider because this is not our criteria. This is not our aim. Our aim is to find out the stress values. We wanted to check the stress distribution and also the maximum stress developed, and we found that in both the cases we got the almost similar results. And here in this symmetric boundary condition, we already told that it has got a lot of advantages. What are the advantages? First advantage will be we can get the result within a very short time, and also meshing will be perfect. As it is a very small segment, meshing will be perfect one, right? Okay, thank you so much for watching this video. If you like, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much. Thank you again for watching this video.